Okay, welcome. We're going over some homework on concavity and the second derivative. So number 17 was the problem f of x equals x root x plus 3. This is actually a good example of the kind of algebra that you have to do to get these problems right. So all right, what we need to do is figure out where, I think the directions are just to figure out where it's concave up and concave down. Is that pretty much correct? Yep. Find the points of inflection? Yeah. Okay, so we do it. This function is the function x plus 3 to the 1/2. And now we will differentiate. So again, just being really careful about stuff. The derivative of this is derivative of the first, which is 1, times the second. So that's x plus 3 to the 1/2. The first and second plus the first times the derivative of the second. And the derivative of x plus 3 to the 1/2 is 1/2 x plus 3 to the negative 1/2 back inside 1. Okay, beautiful. For this particular problem, I don't really care about finding extrema, so I won't even bother simplifying that. I'll just immediately proceed to the next step. And the next step is to take the second derivative. So I just do it. What is the derivative of this? Well, it's 1/2 x plus 3 to the negative 1/2 back inside 1. And now I need to differentiate this, which is going to require another product rule. So derivative of the first, well, what's the derivative of x over 2? Just 1/2. So the derivative of the first times the second. So x plus 3 to the negative 1/2. Plus the first, which is x over 2, times the derivative of the second. And the derivative of this is going to be negative 1/2 x plus 3 to the negative 3/2 back inside 1. So it's just like nice and neat and logical and careful and smooth. There it is. All right, now I have to try to simplify this somewhat. Here I can just combine like terms, so that's just x plus 3 to the negative 1/2. And then over here that's like minus x over 4 x plus 3 to the negative 3/2. Cool. And instead of doing like terrible things with fractions and radicals and crap like that, if we just do it the cool way, we're going to just factor. And so I'm going to take out x plus 3 to the lower of the two powers, which is to the negative 3/2. Okay? And this time I'm getting advanced, so I'm going to deal with the fraction thing at the same time. Because everyone hates fractions, so we just take out 4. And if I do that, then I'm left with some number of x plus 3's. How many of them? Well, 1, because something to the negative, boom, 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 boom. And then I also took out a 1/4 where there was nothing there, so I need to put a 4 back in to cancel that action. Having taken out the 1/4 and the other thing, all that's left is an x. So this method, once you get used to it, it's just really, really easy to deal with. Okay, because now what's the stuff inside here? It's just 3x plus 12. So we get 3x plus 12 over 4x plus 3 to the 3/2. And so my final expression for the second derivative is that it is 3x plus 4 over 4x plus 3 to the 3/2. Alright, this particular problem is a little bit interesting because something that we maybe could have noted at the very beginning, what's the domain of this function? Yeah, the domain of this function is just everything from negative 3 to infinity. So when I go to make my number line analysis for this, I should really only be considering numbers to the right of negative 3.
I guess I just...
And now say something about, like, so what can I say about the denominator of this function then? Yeah, Samin says it is always positive just because, right? Since I'm only allowed to plug in numbers which are bigger than negative 3, then that's just always going to be positive. You raise something positive, 3/2 is still positive. So basically the denominator is always positive. Well, the numerator is just always positive also, as long as x is bigger than negative 3. So we did all this crap. The payoff is like pretty low, right? It turns out that the sign chart for this is just always positive for the second derivative. So this function is concave up everywhere. And kind of makes sense. Does anyone want to say something smart? Why does that make sense that this function will be concave up everywhere? Why is that plausible? I don't even know if it is plausible. Yeah, it's plausible. Yeah?
It's just kind of like a function stretched by a factor of x, so you always have that like general shape.
Like a negative.
No, but this doesn't have the general shape of a root function because the root function is concave down at the beginning. This is concave up. But you're on the right track, yeah, Eo.
But like x grows faster than the root function, like the rate at which x goes up is quicker than the rate at which the root function like slows down.
Yeah, sure. Laura, it's kind of like what you said, but looking at it from the other perspective, it's the x function which is growing at like a line has no concavity, right? A line is kind of like halfway between being concave down and concave up. It's like on the cusp in between those two. So if you think about this function, it's going to be growing at least as fast as a line, but even faster because there's like more. So it's going to kind of look like that. It's going to look actually very much like a line because it's like this is kind of like ish. You can kind of think of this as like x to the 1.5, in the big scheme of things. So it's going to look it's going to be growing faster than a line, but not as fast as a parabola. Yes, but they doing like captains over here. Yeah.
For concave down, does that also mean if there's some constant you can multiply by the x function, where that new function will always be greater than whatever function will eventually become greater than whatever function you have and stay greater than if it's concave down?
Can you say that again?
So I can have like kx, and at some point kx will cross a concave down function and remain greater than it from then on. Is that always true? For some k?
Yeah, I'm going to say yes. If I understand you correctly, then I think the answer is yes. Okay, good. Good, more. More. 24. Let's go fast. You guys are bored. Maybe was this something kind of easy? Okay, let's go fast. We can get to the fun stuff. Here we go. F of x equals sine x plus cosine x on the interval 0 to 2 pi. So we take all the derivatives. So derivative of sine is cosine, derivative of cosine is negative sine, and then the second derivative is derivative of cosine is negative sine, and the derivative of sine is cosine. So we just get this. All right, so now I have this annoying expression. Some of you might boo me, but here I feel like this is just too hard and annoying to try to do anything fancy. I'm just gonna like figure out where it's 0 and then use some test points. That's my opinion. So when is this going to be 0? It's going to be 0 whenever, because this is kind of like negative sine x plus cosine x. So one way to just to think about it, this is going to be 0 whenever sine and cosine are opposite of each other. When does that happen that sine and cosine have the opposite value? 3 pi over 4 and 7 pi over 4. You are all so correct. If you want to be a little bit more methodical about it, you could set it equal to 0. And then you could like move the cosine over. So did some of you do this? I bet some of you did this. And you get negative cosine x, and then you divide by cosine. So then it's like tan x is negative 1, and then you're going to get the same numbers. So now it's just a matter of getting the sign chart right. And I have no deep, cool way to do this. I'm just going to plug in pi over 2 or something like that. If I plug in pi over 2, I get 1 plus 0, that's 1, and that's negative 1, so it's negative, and then someone must be doing this. Cool? Okay. Concave down, concave up, concave down. Alright, faster! 67, I thought was a cool problem, which had you like curve sketching basically, right? So they told you so many things. They told you that f of 2 equals f of 4 equals 0. They also told you that f of 3 exists, but also that the derivative is negative when x is less than 3. F prime of 3 does not exist. Also the derivative is positive when x is greater than 3. And also the function is, the second derivative is negative when x is not 3. Okay, so now it's your job to put this all together into some kind of a picture. let's do that. Here is 2. Here's 4, so it's 0 here and 0 here. So check. F of 3 exists, and the derivative exists everywhere except for 3. So this function must be continuous, I guess, and not doing anything particularly weird. The derivative is negative to the left of 3, so that means the function must be decreasing up until 3, and it must be increasing after 3, but the function is concave down everywhere. So hands always down. So pretty much what are we talking about?
Bird.
Bird. It's pretty much a bird. It's a bird, and then pointy. Something like that satisfies that perfectly. Is that what you guys did, basically? Yeah, but f of 3 exists. That was one of the things. Oh, she did something fancy. I don't see why not. She did an upside down volcano with a dot. That works too, I guess, right? Yeah. She did a super bird. I think that qualifies also, right? Okay, let's do one more. I don't want to do 73 and 75. Which one should we do?
73.
73 was just stupid algebra.
Let's do 75, it's more fun. So 75 says that there is an airplane which is trying to not crash. So there is a plane. I'm a great artist when they provide a picture for me to draw from. Yeah.
Good job.
So now we have a plane which is flying flat and then decides to land. And it is going to land, it is going to begin its landing maneuver 4 miles from the place where it intends to land. And it is going to do all of these actions in a smooth manner. So the plane's going to be flying and then... So that you don't want that to happen. You would like to not crash into the ground, and thus you kind of want it to be like this. And the problem has stipulated that, well, let's just basically call this 0, let's call this -4, and also this height is 1, where the plane is flying a mile above the ground. And so find the cubic function which meets these requirements. It at first seems as if they couldn't possibly be giving you enough information to solve this problem, because after all there are 4 unknowns. But then upon further reflection, there's a lot of hidden information in the problem, such as, Steven?
The min is 0, 0.
Yeah, well, just that the plane actually does end up back at 0, 0. So just that f of 0 is 0, first off, and that f of -4 is 1. Other things that are not explicitly mentioned, but you are supposed to infer from this action, yo.
So D is 0.
Oh, okay, yeah, that's true. As soon as you tell me that f of 0 is 0, I can conclude that d is 0. But other information that's built into the word problem, yes, Amin?
Isn't the point of the function like in this sense? I don't know. People make it try.
It certainly looks like that that's true, yeah. But, oh, you used that? Oh. Use this.
So you know that the derivative, if it has to be smooth, that means it sort of has to go flat at the beginning and the end. So that means that the derivative at -4 and 0 are both 0.
Yeah, that was the key thing that you have to get out of this, right? If the plane is flying like this, if the plane's flying flat, then at the point where it begins its descent, the derivative here is 0, because the elevation's not changing, and then it starts to change. And also at the point where it's landing, it shouldn't be changing the elevation either. It should be... So the other pieces of information are, yeah, that f prime of -4 is 0, and also that f of 0 is 0. And once you figure that out, now it's just a matter of doing it. F prime is 0. So what is f prime of x? F prime of x is 3ax squared plus 2bx plus c. And since f prime of 0 is 0, that means that c must be 0 also, right? From this I learned that c is 0. Are we cool with this? Without me writing all the details? Alright, and then the final one, if f prime of negative 4 is also 0, then if I plug in negative 4 into the derivative, I get 48a minus 8b has to be 0.
Wait, what happened?
C I just included as 0, but since f prime is 0 is 0, if you first plug it, cool.
Yeah.
So that's really like, if I divide by 8, that's like saying 6a minus b is 0. So b is just 6a. And now to figure out the relationship between a and b, I need to use more facts. Oh, I need to use the only other fact left, right? Which is that f of negative 4 is 1. So if I plug in negative 4 into this, I get that f of negative 4 is negative 64a plus 16b. That's it. That has to be 0. No. What am I doing? 1. It has to be 1. Cool. So that means negative 64a plus 16 times 6a is 1. So 96 minus 64 is 32. So if 32a is 1, then I know that a is 1 over 32, and b is 6 times that. So b is 3 sixteenths. That's pretty much it. Cool, make cool. All right. You guys seem kind of down. Is this like quarter's over, but spring break hasn't started yet? So you're just like it
What's
just,
the point of this
just
week?
feels like unfair.
Yeah.
It feels just like a.
Unfair, it's just- there's no
You're
point.
just used to everything being unfair all the time. It's like life.
No, it's just,
What?
there's no point at this point, like, at this time right now, there's no point to really.
Exactly.
Yeah, we're not even
Excited
gonna
to
remember
try
this.
It's true. That is actually true.
Well,
That's how you
if
get a
forget
packet
it,
for
you
spring
can
break.
watch the video. All right, good. Let's have this homework, and we're gonna do something fun. I might do something fun and cool and creative next that I've never done before.
Outside.
No, we're
It's
definitely
so
not
nice.
going outside.
Why were the only
Gunpowder is like fun.
That's not true. I've not gone outside.
Should we, I guess we'll just keep recording. I went outside in period 3
Yeah,
one
why
day.
can't we go outside?
Oh, well, we got there. Maybe we can.
Yes.
Probably not though.
You said definitely not.
Good. Put it in a pile like over there seems like a good spot.
Meaning like, oh, what?
Just happened.
We're not fixing it.
Yes, I did know that.
I'll tell you later next week. Oh my god.
All right. So, differentiation's really cool, but what we're gonna do now, we're gonna open up a whole new window into an entire other category of problems that you could not have imagined in your wildest dreams.
That's a Taylor Swift song called Wildest Dream.
Oh,
It's a great song.
good. I planned that. So what I want to talk about is actually that was everything I just said was a total lie. What we want to talk about is optimization, and this is in fact something which you are experienced with because optimization is something you did for about 2 weeks in pre-calc A. Do you remember this, Giles?
I don't know why.
Yeah.
Expect us to remember this stuff.
Yeah, I do. All right, let's have a little refresh. It was only a year ago. Let's have a little refresher. So let's pick a problem that speaks to your generation. Like we'll do something about farming because that's the background that you guys all have. So suppose you have a farm And you, what animal would you like this one?
Turtle.
Cow.
Rabbit.
Otter.
Chickens.
Whales.
Pig. Otter.
Okay, we'll do
Pigs.
Otter.
Everyone says pig.
pigs. I guess we'll do pigs.
Are we
No.
farming the pigs to kill them?
It's unclear what we're gonna do with them. Okay, so we have a bunch of pigs, and we want to make sure that they don't get away. So we have to build a fence for the pigs. So let's suppose initially, Raymond, let's initially suppose that we have acquired some fencing, and we would like to build a rectangular enclosure in the middle of a wide open pasture, so that the pigs may like frolic and like eat grass. I don't even think pigs do. Pigs eat grass? I feel like not.
They eat
They eat
everything.
slop.
In this, they like slop. Yeah. It's a pasture of slop. It's just slop as far as the eye can see in every direction. The ground is made of slop. So the pigs are going to graze, and they're going to eat slop. It's a great word. We really need to use that word more often. They eat grass
I
too?
told you to be otters.
Yeah, they can just eat anything, yeah. That's the great thing about slop. It's just anything you want it to be. So, anyway, so, Raymond, what shape would you choose to build your rectangular enclosure in, seeing as how you would like your pigs to have access to the most slop they can? Yeah, I said rectangular. Yeah.
Wait, what?
Okay. All right. So you were supposed to like. We were supposed to be leading up to that. But yeah, Raymond, why aren't you answering?
Because it's just a rectangle.
Yeah.
Square.
But what kind of rectangle?
Oh,
You said it was a rectangle.
Yeah, square is a rectangle. That's like
Wait,
math.
what?
Okay, wait, hold on. This,
I thought you
this,
said we're building
this
this.
did not work as I intended it. Let me try again.
You said what type of rectangle?
Yes,
Oh, you
exactly.
said what type of shape, so I was like,
I'm sorry.
I was
Okay,
confused.
try starting all over again. Striking the previous minute and a half of the record. Yes, you are all correct. If I have decided for whatever reason to build a rectangle, what kind of rectangle? Answer.
Square.
One of those square type rectangles. Yeah. Because why, Raymond? Why?
Because it would maximize the area.
Because it would maximize the area for a given perimeter, he claims. That's just kind of common sense. That's true. We can prove that. Let's not bother. Yael says, screw this. I'm going to rebel against this problem, as I do through all things. I'm not going to make a square. I'm going to make a circle. That's because a circle more efficiently uses perimeter. In fact, for a fixed perimeter, you can do the circle is like the best you can do. And actually, that is a fake calculus generalization from a more particular theorem, which says that, first of all, within any particular type of polygon, so like suppose your polygon must have n sides, like say 7, you want to build a heptagonal pig slop enclosure. Well, it is the regular 7-gon which will maximize the area for a given perimeter versus any other kind of 7-gon. And then also, as you increase n in the n-gon, it gets better and better, right? So a hexagon does a better job than a square of maximizing area. You guys all with me? This is like kind of common sense. You've thought about these sort of things before? If not, you're thinking of it now. All right. So the limiting case of that is a circle. All right. That's all kind of boring. What if now, instead, you decide to try to save money on fencing and also increase the amount of slop available to your pigs by building your rectangular enclosure along a river of fire? Or, I don't know, what do you want to be in the river?
Acid.
Otters.
Whoa, okay. Flaming radioactive acid.
Yes.
Otters.
Flaming acid.
Acid with also alligators. Okay.
Flaming radioactive.
No, not alligator. Otters.
Too late. Generally speaking, you do not have to worry about your pigs getting in there. And so it serves as a fourth wall.
I think that's more dangerous.
So, this is the kind of farming I'm used to. I don't know about you guys. All right. So, now I'm going to build this rectangular enclosure And we have just 100 meters of fencing total. Don't shout out your answer. Mentally make a guess. Drawing it on your paper, first mentally, then on your paper. Guess the dimensions of the rectangular enclosure that will maximize the area. Go. You have 5 seconds to think and label a...
Wait, can you say the thing again?
What does that
Say it
say?
again?
Just guess what the dimensions are of the rectangular enclosure given 100 total meters of fencing, which will give you the most area. No time for thinking, just like make just an instant guess.
No, that's it's rectangular.
It's a rectangular.
Actually, no, actually, you just do this.
Because you don't need it.
Yes.
No, because the areas.
Just make it. Oops, sorry. Just make an instant guess. All right.
Yeah, but then that means you're also going to be maximizing the other side of the rectangle.
Okay.
as well.
Did you make a guess yet?
What was it? Right? With R is, let's say R is this, right? Versus
30, 40.
I,
Interesting.
R.
Okay. A lot of you said do 33 1/3, but now Busis retracts.
Yeah, I was going to say
Yeah,
10.
so that is an idea because the square principle seems to indicate that squares are good. But, says Laura, let's see, I'll call this y and I'll call this x. Says Laura, I think I heard her say something to the effect of, well, as we are building the rectangular enclosure along our flaming radioactive acid with Alligators River, we get one side for free. And so every meter of fencing in the x direction, kind of, you get like a free meter for everyone. So maybe it should be longer like this, right? Because I only have to build one wall for how big it is in this direction, whereas that's a bit cool. So y is more expensive or something like that. So I think that will come into problem. All right. Anyway, let's just do it. You all did this problem, and this is an algebra 2 problem essentially. This is not even a calculus problem. What do we do?
Area equals.
Y. 2y equals 100.
Okay, right. So fact number 1 is that 2y plus x equals 100. That's just true, because I told you the perimeter is 100. And it is also true, says Busis, that the area, after all, which is the thing that we're trying to maximize, is xy. And just like with the related rates thing, it would now be convenient to express the area not as a function of 2 variables, but as a function of 1 variable. So like, you know,
X equals 100 minus 2y.
get rid of one of them. Which one do you want to get rid of?
X.
Y.
X.
Y.
X.
Y.
Oh.
I want to get rid of x.
Yes.
Because it's just prettier. That can avoid fractions, I guess, right? So x is 100 minus 2y. So what is the area now expressed as a function of y only? Is everyone cool with this? This is like easy stuff pretty much. Is 100 minus 2y times y. And damn, what do you know? That is a parabola. So this is an area, this is a function, which for a given y will tell you what the area is. And then what would we like to do with this function, therefore? Okay, that's one thing I could do. But yeah, more generally, I want to just maximize it, right? Because I'm trying to, I didn't write down what the actual problem was, but the problem was to find the dimensions which make the area as big as possible. So if I want to make the area as big as possible, I just create the area function and then I maximize that function. Well, as it turns out, I don't even need calculus to do this problem because it's just a parabola. So the way you guys did this last year, I guess, is like, what it was, I mean, it's like factor and stuff. That's one way. You can do negative b over 2a, you can complete the square, or you can just, what I'll do is I'll just factor out a negative 2, and then that becomes y minus 50. And now I can just like draw a picture. This is an upside down parabola with a root at 0 and a root at 50, and thus by like facts about parabolas, the vertex must be at 25. Cool, cool?
Yes.
And you did a bunch of problems like this, I guess. You know, it's called quadratic optimization. All right. If you wish to, you know, turn away from the past and use like the new, as in the last 400 years, techniques of calculus to do this, you could just not bother, you don't have to know anything about parabolas per se. You could just take this area function and write it as 100y minus 2y squared, differentiate, so we get, dA dy, and that is going to be 100 minus 4y, right? And that can also be factored as negative 4y minus 25. And then if I make a sign chart exactly like what we've been doing, the A prime sign chart, well, it changes sign to 25. And that negative 4 up there means it's an upside down line. Is everyone cool with this? So it's plus, minus, and our new techniques tell us that since the derivative of A with respect to y changes sign from positive to negative at y equals 25, then there's a relative max at y equals 25. So, okay. All right. So that was called accessing prior knowledge. Samin, you did this crap back in 9th grade. Now we're just doing it all over again. The new change is that I do not have to restrict myself merely to problems which turn out to be quadratic, right? Now, for any function whatsoever, as long as I can differentiate it, then I can find the maximum. Cool? Okay. So now's the time to do something fun, maybe.
Go outside.
Going outside is not as fun as you would think. Okay. Okay. Alex. All right. So I tried this yesterday. I thought it was okay. Well, let's just stay positive. All right, Steven. I'm gonna try something cool. It requires you guys to be like creative and like engaged. Though. You can do that.
I can do it.
If we go outside.
All right.
You don't get any
Right.
sunlight.
Okay. So all right, Mateo. We are a company. And we are going to make oil cans.
Is this like a sweatshop or is it like an actual business?
That's a really good question.
This is like child labor.
We're inventing this as we go along. We have not yet acquired, well, I don't know, it depends. Do you want it to be a sweatshop?
Yes.
Yes.
Okay.
Can I
So
record?
apparently it's a sweatshop. And it is going to be made in well, whatever. It's a sweatshop, and we're going to make. All I care about is that the cans be cylindrical. The rest is really up to you.
What?
All right. So, and there's. Oh, by the way, there was some confusion yesterday about this is like oil can. I guess it doesn't matter how we interpret the problem, but I was thinking of it more as like cooking oil, but it could also be oil for car. It really
I
doesn't
thought
matter.
it was.
That's what you thought it was? It really doesn't matter.
What type of
What?
I think you're drawing
oil
off.
doesn't come in a
It's really
can?
weird.
Cooking oil doesn't come
So, good. Mateo, tell me something about what kind of shape I should make this oil cannon. Just say one thing. It doesn't have to be about math.
Should be cylinder.
Oh, besides a cylinder. That's the only thing I told you has to be true. It has to be a cylinder. What kind of cylinder though?
Are there really kinds of cylinder?
There are lots of kinds of cylinders. We're having open discussion.
I'm not sure.